Okay. All right. I think we're recording now. Okay, perfect. All right. So yeah, today we are going to talk about network virtualization. But before we talk about that, let's try to quickly recap what we learned in the previous set of lectures. So we were talking about network operating systems, and as we learned that network operating systems instantiate the distributed state abstraction, which is very critical for software-defined networking, right? And we looked into various challenges that these implementations or realizations have to face, mostly related to scalability and ensuring consistency between different replicated state. In other words, I would put it this way, that scaling these network operating systems required a forced to have a distributed instantiation of these network operating systems, and having a distributed, realizing them as a distributed system basically entailed all the problems that distributed systems have to deal with. But the good thing is that you don't have to apply all that sophisticated logic of distributed systems in a switch. So switches can still remain dumb and do the only task which they know better, which is packet forwarding, right? And all the intelligence just moves up in the user space. And now you can apply all these distributed algorithms to figure out how do you maintain a consistent view of the network, what view you offer to the users such that they can write meaningful control programs, and how do you ensure that, how do you handle conflicts that might arise if there are two control programs trying to access the same network state, either reading or writing to the same network state, right? And we learned about all these different approaches that people have come up in the area. And we specifically focused on Onyx and ONOS as two instantiations of this idea. And we know that Onyx was something that was pushed heavily by Google in the formative years of software-defined networking. And ONOS was something that came around 2014, but it's something which is open source, publicly available, and actively used even now. Okay. So this is kind of like the overview of what we learned in the past two lectures. Now let's talk about network virtualization. But before I do that, I think I realized that there were a couple of questions that are worth discussing in the class from the quiz. And I just made sure that, like the 2 p.m. deadline, no more responses are accepted. So thanks for participating. And, this is a snapshot that I took maybe a couple of hours ago. So this is not don't read too much into the numbers that there are 27. I think there were 40 plus responses. So this is a bit old view of mine about which problems or which questions were a bit challenging. But most of you did fantastic. So kudos for that. But I think there were a few questions that maybe were confusing. I figured that it's worth discussing so that moving further you don't have these confusions. So the question was, Onyx decomposes switch state across different instances. Okay. And majority of you got it wrong. Okay. So, but there were like 48%, at least 2 hours ago, there were 48 people, 48% of you who got it right. So maybe one of you can attempt to explain what this question means and why is it correct? Why is it not correct? Come on, there are 13 of you who got it right. So I guess some of you were confused about the language itself. So maybe if you have confusion, maybe you can speak up as well about the confusion. Okay, so so Victoria got it right, but she claims she doesn't understand the statement. Okay. Anybody else? So maybe I can take a pass here. So, 2 lectures ago, we were talking about how Onyx is, scaling, or ensuring that there is scalability. And one thing that is key to Onyx is that it is trying to partition the state across different instances. And the design choice that Onyx made is that it can partition the forwarding state so that the forwarding state remains local to a particular instance. It does share the forwarding state with the other NIBs as well, but that is not something which requires a very high urgent consistency requirement, right? But for a network control program to write meaningful programs, it has to have this full view of the network. So that is abstracted as switch state, which is like, which switches are on, which links are up, which links are down. So that is referred to as the switch state. And switch state is not partitioned, right? So every instance, maintains a consistent view of the switch state. Okay. So the question was, Onyx decomposes the switch state across different instances, which means is Onyx basically partitioning the maintenance of the switch state across different Onyx instances? And the answer is no, it is not. It is partitioning the forwarding state, but it is not partitioning the switch state. Okay. So did that clarify things for you folks? Okay. All right. So the other question was, Onyx offers virtualized network view to the control programs. And I think majority of you got it right. So maybe one of you can try to explain why this is correct, or why false is the right answer here. Exactly. So Tianroy, maybe I got your wrong name incorrectly, but Tianroy is saying that the understanding is that virtualization is not offered by operating system, and that is correct. That the Onyx especially is not offering any specific virtualization. It is not virtualizing the physical network to the control program. It is offering the control, it is offering the physical state of the network as is to the control programs. And then it is up to the implementation that we have as a control program about how you use that physical information. Do you write programs directly on the physical network, or you add a virtualization layer at the top? That is up to the users of that operating system, or how northbound API is getting used. But Onyx by itself is not offering any virtualized view. It is offering the physical network view, or access to the physical state of the network directly. Okay. So any confusion on this? Can we move on? Okay, thank you. All right, so there was one more question, which I think almost all of you got it right, but I felt there was still some reasonable fraction of students who got it wrong. So PISA switches do not support stateful operations. Can anybody want to explain why this is a false statement? Remember, PISA switch has these identical compute stages that it uses to process the packet header vector that is coming into the switch, right? So a PISA switch has this ingress port, then you have a programmable parser. This programmable parser is converting a packet header into a packet header vector. Now this packet header vector is traversing across multiple identical compute stages. And then at the end, there is a deparser and the packet is serialized back, and then it goes out, right? So this is what the PISA packet processing pipeline looks like. Now, we in each stage, we have ALUs and we have SRAM, right? And SRAM is very important because SRAM is the one which is used to maintain state, right? So if I see a particular packet, I can extract some information from that packet and store that into the SRAM. And when the next packet comes in, I can actually use the stored information to do something like apply some action, right? I might maybe want to compare the timestamp of this packet one with the next packet and take a difference, right? So this is an operation that I might want to do. But for doing this operation, I want to store the timestamp of the first packet itself, right? So this is an example of a stateful operation. We are maintaining the state in the network and supporting these stateful operations. So PISA switches, given that they have the support for memory in each of those compute stages, they are capable of supporting stateful operations. Okay. Questions, confusions? Okay, I think we can move on. I noticed that almost all of you did very well in this quiz, but nobody said that it was easy. And I was just trying to get a sense of, whether the questions were too obvious given what we were discussing in the lectures. But either all of you are very humble, or you're tricking me here. But what the question is, what is the average score? I can tell you the median score. Give me 1 sec. So median is 23. So almost, like majority of you were able to do like answer 23 out of 25 correctly. And again, take that with a grain of salt, because this is only up to the point where I had 27 responses. Well, actually, no, I take that back. So the score that I see is for all the responses that I have so far, and the median is 23. So that is a very high median. And I've personally reached out to those of you who, didn't had that well of a score, and we will talk about what challenges each of you are facing. But otherwise, I think it looks like based on these quiz scores, majority of you are able to follow the key concepts and understand these fundamentals of software defined networking at a much basic level. So that's great. Kudos to all of you. So Charles is saying he had to do a lot of reviewing. That's good, not bad. Okay, so it was fairly difficult. Okay. So what was the average time effort involved here? So is this a lot of significant fraction of your time that you had to invest in it, or are you facing issues because this is requiring a lot of workload for you, not along the lines of what I promised earlier? I can turn it down if this is a lot of work. Okay. I don't know, how is this an assignment? Wait for the assignment is what I will say. Okay, so what I can do is that maybe I can reduce the number of questions moving forward. So that might reduce the total amount of time that you have to invest here. Okay. Okay, I think reducing the number of questions moving forward should help you manage the workload better. I don't want you folks to hate the topic just because it is taking too much of time. I've been an undergrad myself. I know time is scarce, so let's not make it an overburden for you, especially as we move forward. You'll be spending a lot more time on the programming assignments, so I don't want this quiz to be a huge burden for you. So I'll maybe restrict the quizzes to maybe 10 to 15 questions. So that should be small enough to attempt, and we'll take it from there. If there are challenges, then we can talk about how we can calibrate. All right, let's move on. So what are the learning objectives for today? We are going to talk about what exactly is network virtualization, what does it really mean, and in what context it is applied, which is the multi-tenant data centers. And we will specifically try to understand the requirements for these multi-tenant data centers and how exactly a solution called network virtualization platform was designed, and what type of challenges and issues it had to deal with, and how it addressed those challenges. So in today's lecture, I'm not aiming to have this complete coverage on the NVP platform, but I think we will be talking a bit more about different abstractions and how those abstractions are getting realized, and maybe briefly talk about some challenges associated with that. And then in the next lecture, we will talk a bit more about the scalability challenges, especially from the control plane perspective. And as we move forward in the next lecture, we will talk a bit more about the application of virtualization in context of networking prototyping or networking research. And that's something which is more related to the assignment that you're working on, where you're using Mininet, which is an instance of a network virtualization, and you're using that for reproducible networking experimentation on a laptop, right? So we'll talk a bit more about that in the next lecture. All right. So abstractions, as we know, are very critical for any computer systems, right? So when we talk about virtual memory, abstraction is the key here. That I'm accessing memory without really worrying about where exactly the memory location is, or is this how exactly I'm going to access that memory, right? So when you are given an abstraction of virtual memory, you're given an illusion that you have infinite amount of memory that you can work with, and you don't have to worry about where exactly this memory is, how exactly I'm accessing it. Same goes with the file system, that when you are given this file system abstraction, you're working with the file system, you deal with the APIs, the program interfaces, open, read, write, close, whatever, right? So these are the abstractions that you work with, and you don't really care about which physical location where exactly this file is stored, how exactly you're going to physically read from that location. That is all abstracted away, that all those details are abstracted away, right? And then we talk about the virtual machine. So in context of virtual machine, when you're writing or when you're running an application program on a virtual machine, the program cannot differentiate whether it is running on a physical server or it is running on a virtual machine, right? So the like all the details about how exactly it is going to access different peripherals, how exactly it is going to access file systems, like you name it, everything that is relevant to operating system, everything is virtualized, and the application program cannot differentiate whether it is running on a physical compute machine or a virtual compute here, right? So like this is something that I've been uh, repeating multiple times in this class, is that abstractions is the key when you're trying to build some like impactful, meaningful systems. You have to always think about, do I have the right abstractions? And maybe if you're solving a very difficult problem, coming up with the right abstraction the first go is not feasible. And as we saw in previous iterations of software-defined networking as well, people didn't get the abstraction right in the first go, and it took multiple years of iterations before people could converge on the right abstraction. But here we are. I think none of these abstractions that we're talking about right now were were instantaneous, right? So everything took time to evolve. Virtual memory, file system, virtual machines, everything took time. But the past 1 decade in the networking community has always been finding the right abstractions for the control program, right? And that has been the evolution of software-defined networking as we study in lecture 2, right? So now when we talk about virtualization, recall that we talked about this specification abstraction in context of software-defined networking. We said abstraction is a simplified model of the network. And when we're trying to express the control program should only configure the abstract model of the network, not the actual network, right? So as we were discussing about the abstraction offered by the Onyx, so Onyx is exposing the physical network to the program, right? So it's not offering any abstract view of the network. It is just exposing the raw network, physical network to the program. But that will just make it very difficult for a control program to write these programs, right? So think about it as a assembly language versus a Java or a Python language, right? So if I have to worry about each and every physical network, then I'm really going to be very slow in terms of how flexible, how powerful, strong programs I can write. Versus if I have these virtual abstractions about, I have a virtual view of the network, I don't have to worry about each and every physical element in the network, then I might be more efficient in terms of writing those programs, right? So this is close to what that specification abstraction is all about. That when you're configuring the network, you should configure the abstract model of the network and don't worry about the full physical network below you, right? And to realize that, we require a shared network control layer that is able to provide the mapping between the abstract configuration that you are specifying and the physical configuration that the devices really need, right? So if I specify an abstract configuration, that will somebody has to be there in the middle that is doing the translation job of those abstract configurations to physical configurations, right? So what is that control layer? That is basically the virtualization layer that we are going to cover, right? So let's try to understand that a bit more visually here. We have the data plane. Right now, what we are looking at, it just looks like that these are hardware data plane targets. But as we know, the data plane targets can be software, it can be hardware. We have a network operating system which is interfacing with these data plane targets using the southbound APIs, right? Now, this network operating system is exposing a global network view, right? And if we look at the reference for Onyx, then the global network view that Onyx was offering was through network information base, NIB, right? That was the exposure that Onyx was giving to the control programs, right? So this is kind of like what we studied in the previous set of lectures. Network operating system, global network view. And when we talk about Onyx, that is basically NIB, right? Now, when we talk about network virtualization, what happens is that now we are adding a virtualization layer in between the operating system and the control programs, right? So now, rather than offering this physical view to the control programs, this virtualization layer can afford to offer a virtual view of the network, right? And we will study why this virtual view of the network is important and meaningful, especially when we are trying to write these sophisticated control programs. But being able to slice and dice the network in such a way that a particular control program only has to focus on a small subset of the network just simplifies things greatly from like writing these control programs perspective, right? So I can write these control programs that are closer to my intent rather than closer to what the physical state of the network is, right? So this is what network virtualization is offering, that it is offering a virtualized layer, control layer, which is like exposing a virtual view of the network to the control program that is simplifying how they write the control program. And the job of this virtualization layer is to do the mapping between the configurations specified in the apps on the abstract model of the network to the physical network, right? Now we have some questions here. What's the difference between virtual and physical view, and why doesn't the control program just only look at the slice it wants? So I think like these are good questions, especially I'll take the last one first. So why doesn't the control program just only look at the slice? So people tried that, right? This is a very natural way of thinking about the problem, that if a control program's only job is to focus on a certain slice of the network, why can't we just expose that slice to the network and they can write these control programs? Yes, this is a logical thing to do, and people tried that. And then we will discuss today that like why that can be a challenging, especially in context of multi-tenant data centers, right? Which was a big driving force for all these techniques. The other question is that what's the difference between the virtual and the physical view? I think you can view it in multiple ways, but think about it from two perspectives. One is the topology, that like what we look at in this figure is a physical topology where we have four forwarding devices, right? They can be hardware targets, software targets. Let's not get into that. So these are this is the physical topology that we have. Now virtual view can be that it can offer a different topology to the control program, right? And that topology might be a subset of it. It might be like completely different topology that can be realized on top of this physical topology, right? And we'll get into the details of that, but I think that should give you a gist of what is a virtual view and how is that different from the physical view. Okay, so that is one example, which is topological difference. The other is the address space, right? So the addresses that we have in this physical network right now, with this virtual view, I can offer a completely different address space to the control program. They might be completely offering in a operating in a completely different address space. And as long as I have this virtualization layer that can do the translation from virtual view to the physical view, I can support that virtual addressing as well to the control program, right? So how are these two different? These are two different in terms of topological differences, that I can offer a completely virtual topology that they can operate on, and I can offer a virtual address space that they can operate on, right? And this is how the physical and the virtual views might differ in these settings. Did that answer your question? Okay, perfect. All right. So this is kind of like illustration of that. Notice that when I'm like when we're talking about these different control views, control programs, then they're operating on different views, right? And views can be different view in terms of the topology, different view in terms of the address space. And you can see that, like this illustration is actually emphasizing the point that these are different topologies that they're operating on, right? It's really hard to put address space in there, but like they can also differ in terms of the address space. Okay. So let's try to get the definition a bit more precise when we talk about network virtualization. So the abstraction or illusion of a physical network in which the user application cannot tell if the network is physical or virtual. That is network virtualization, right? And I'll give you 2 seconds or 5 seconds to just soak that in, right? What we're talking about is that when we say network virtualization, we are providing an illusion, not an actual physical network. We are providing an illusion of a physical network to a particular user or an application such that they cannot tell whether this is physical or virtual, right? So this is the precise definition of network virtualization. Okay. So we are talking about the virtualized network here, right? And I'll try to differentiate between virtual machines or virtual compute versus virtual network, right? But what we're talking about is the like what we see here at the bottom, that is a physical network with certain set of devices. I can offer a virtual network which is realized on this physical network but looks very different from this physical network. Okay, so compute is different, and virtualization of compute is basically enabled via virtual machines or Dockers, right? But the virtualization of network is enabled via virtualization, like network virtualization or the tools that we will be learning. Okay, all right. So some of you are familiar with VPN. How does VPN work? Can anybody want to take a guess here? How does a VPN work? Did you learn about VPN in 176A? Okay, so let's take one step back and let's try to reason about, like, is anybody familiar with what VPN is? Has anybody used VPN? Okay, some of you have. Yes. UCSB VPN, if you're trying to access campus resources remotely, you're using UCSB VPN, great. If you are trying to access content that is restricted in your country, then you might be using a VPN of some other country and try to access that content. This was something which was very popular before Netflix and all those things were there, but yeah, different eras that we live in. But point is that what is a VPN? VPN is basically providing a tunnel between the client and the server such that it can, bypass all the, it basically abstracts away all the nuances and details about the forwarding path, right? So in some sense, it is virtualizing the forwarding path between the client and the server, right? So whenever you are trying to use VPN, you have a VPN server, you establish a VPN tunnel between the client and the server, and all the traffic between the server and client is encapsulated in these VPN headers, and then it goes out, right? So even if you're sending a browsing request, any network device in between cannot determine that this is port 80 traffic or this is port 443 traffic or whatever, because this is all encapsulated and encrypted. So all they see is that there is some communication between VPN client and VPN server, that's it, but they don't know what exactly is the content, what exactly is being requested, right? So VPN is a very, very popular service, but the question is that sorry, I had a visualization here. So you're doing a web browser, you have IP datagram, right? And then this IP datagram is pushed inside another IP datagram with tunnel header, and then that is going through the VPN, through this tunnel to the VPN server. Now, the question that I was getting at is that to what extent is this virtualization? Is this the virtualization that is relevant to software-defined networking? If not, then why? Maybe I should ask a simpler question. Is this virtualization? Yes. So I think, okay, the answer was not yes, the answer was yes. uh, so yes, I think like it is a type of network virtualization because it is abstracting away the physical forwarding path, right? So it is encapsulating the packets, it is abstracting away the physical forwarding path. But when we look at it from the SDN perspective, software-defined networking perspective, there is no virtualization of the control here, right? So like it is, in some sense, you can think of that as a virtualization abstraction for the data plane, but it's not really a virtualization for the control plane here, right? There is no control plane virtualization here, right? And what does that mean? We will revisit this question later, okay? But the the point is that, you know, like we cannot say that this is not virtualization. This is a type of a virtualization, but is this a virtualization that is meaningful from software-defined networking perspective or not? That is a different question, and we'll revisit that question later. Okay. Now, as some of you were suggesting that, hey, like, you know, why don't we just slice the network and offer a different slice of the network to a different control program, and each of them, as long as they're operating on their own slices, and we can, you know, ensure that they're operating on the same slice, that is a good network virtualization, right? And I'm trying to recall who made that point, but okay, I'm not, anyways. So point is that, you know, one of you already suggested that we can slice the network and offer that sliced view to the control program, and they can just, you know, make sure that they're only operating on this slice. And this is actually a very intuitive idea to go with, and was used by a lot of solutions. So what I'm like, you know, what I'm referring here is a network slicing solution called Flowvisor, which was reasonably popular during the OpenFlow era. And what it did was that it offered this slice of network which was separate in terms of flow space as well as topology, right? So when I say flow space or header space, it's the same thing. That you remember we had these multi-dimensional space defined based on the packet header field, right? So like what this slicing was doing was it was defining some spaces in that flow space that, okay, you know, like range of destination IP X to Y, you know, you can operate on it, right? So this is the address space virtualization. And then it also virtualizes the topology that, okay, I have these, you know, 5 links in my network. I can create a topology with these 5 links, and you can operate on these set of address spaces. So that is your slice to work on. I can have another one, which is maybe only using 3 of these links and a set of, you know, another set of header space, and then like that, right? So basically it was offering a bit of a virtualized topology, and it was also offering this separation in terms of the address space. But there is still a problem here, right? Can anyone point out what is the problem here? So like, you know, this is a good question. Like we have a question where Garrett is asking that since the network operating system maintains the network state, how can Flowvisor operate between the network and the operating system? That's a great question. So I don't, like, if I remember correctly, Flowvisor was not compatible with Onyx, right? So that choice of consistent network state is a very Onyx specific choice, and I don't think the Flowvisor was designed to be compatible with Onyx, right? So that is point number one. But I think, like, you know, what is more troubling to me is that the virtualization layer is between the operating system and the data plane targets, right? So this is a bit of a you know, like inflexible virtualization, that there is a limitation of how much virtualization is possible in this context, right? Because you're basically tied to the physical topology more if you have the virtualization layer sitting in between the open flow, like data plane targets and the operating system, right? So in a sense that like you have to have this physical separation of the address space and physical like reliance on this existing topology, that it was limited in terms of flexibility that this type of virtualization was offering, right? But nevertheless, this was a reasonable virtualization solution that worked well for a lot of enterprise settings, right? So this was basically designed from enterprise networks in mind, and it worked well in those type of settings. And it was actually like, not exactly the flow visor, but like ideas related to flow visors were adapted, and they were like, commercial solutions that were offering something similar. Now we will revisit that and try to reason about this flow visor concept in context of multi-tenant data centers, right? So we'll get to that soon. But keep that in mind, that like this is how the flow visor actually operates, that it is basically slicing and dicing the network, both in terms of the topology as well as the address space, and then it is offering that sliced view of the network to the control program. Okay. And let's revisit this question about to what extent is this virtualization. Now let's get to the main point about the data center networks. So data center networks, when they initially started, it was all about that, okay, like these are homogeneous set of compute servers that we'll just deploy and then use these compute servers to scale up, like, do elastically scale the computing tasks that we have, right? But over time, what happened was that there was this diversity in workloads that the data centers had to handle, right? So there were some use cases where the data centers were used for analytics tasks, and then they were also used for hosting web applications and also doing a lot of background processing and computing, right? So when we have these type of workloads, different workloads, like you might want to have their own set of requirements in terms of where exactly this workload has to be executed, on which physical server it has to be executed. So there are like these requirements in terms of how do I partition these tasks, and how do I make sure that these tasks are still sharing the same set of physical resources, right? And that is where the virtualization of compute became very prevalent, right? So now, rather than treating this like these servers as homogeneous compute resources that were used for just one type of processing task, now we have different type of applications and processing tasks in place, and that motivates that the need for having the virtualized compute abstraction, that like you treat this as you have infinite pool of compute resources, and then you just decide that where exactly or how exactly you will use this resource, right? So now we when we refer to multi-tenant data center, you can think of it in terms of that there are these different physical tenants that are sharing these compute resources, or you can also think of them as like different applications that are sharing these physical resources, right? And the network, like the compute virtualization, the virtual machines basically provided great abstractions that these virtual machines running, they couldn't differentiate whether they are running on physical servers or they are running on virtual machines, right? So this was the success of the operating system virtualization that enabled this resource sharing and enabled running different type of VMs, different type of workloads on the same physical server, right? It was very important from the cost perspective. Now the question comes from the networking perspective, right? So what are the real requirements of networking for these multi-tenant data centers? Can anybody want to give a try that what type of requirements these tenants that we have in the data center have from the networking perspective? What do they need from the network? So I think okay. So topology, yes. So let me elaborate a bit more on the topology part, right? So as we said that these virtual machines can belong to different tenants. they can belong to different applications, right? And these different tenants or applications might have different topological requirement, right? So if it is an analytical application, right, analytics related application, it basically need a topology which is supporting L3 routing, layer 3 routing, right? If it is just an enterprise application, then it might just require, like just one hop connectivity for all the virtual machines, right? So in some sense, it just requires the L2 connectivity, that every virtual machine is just directly connected to each other over the layer 2 network, right? So all you need is just the MAC address of the other VM, and you should be able to connect, right? And then there are these web applications that are tiered, right? So you first like have these like the gateways that are that are basically processing the requests coming in. Then you have the backend servers, then you have further backend servers, right? So you have this hierarchy or multi-level processing that you want to support. So that requires a completely different type of topology, right? So there is a diversity in the topological requirement that we have from the network. Okay. So we have this physical network. Can we support different type of topologies on this physical network? How, and if yes, then how? Can I use this physical network that I have to support L2 switching between yellow VMs, L3 routing between green VMs, and multi-tier routing between blue VMs? Okay, I think let me have that thought soak in for you folks. What we're talking about is that from the compute perspective, the operating system virtualization that happened is offering this this feeling that, oh, if I have this task one which is related to some type of enterprise computations, the other is some analytics stuff, the third is some web applications, right? So I have these different set of tasks at hand, and I have this I don't worry about the compute resources. I have compute resources available for me through these physical servers, right? But now I have these different type of networking or connectivity requirements between these compute nodes, right? So I have some requirements from the network, right? So if I'm running an analytics task and I have this requirement that I want to connect these different nodes, virtual machines, using layer 3 routing, right? So I want to support this layer 3 routing between all these different machines. So that is my requirement from the application perspective. For a different set of application, I have a requirement that all these, virtual machines should be directly connected with each other, right? Like using a layer 2 switch, everything should be just connected directly to the layer 2 switch. Okay. And then I have this other set of VMs where I have the requirement that I want this multi-tier connectivity, that, at first tier, these left 2 VMs should be there. And then at the next tier, these other 2 left should be there. So I have these tiered requirements, multi-level requirements from the topology perspective, right? So in some sense, different workloads have different topological requirement. I have this physical topology. Is there a very easy way I can support that? Can I use Flowvisor to do that? Can I use Flowvisor, which is what we covered here? Can I just use Flowvisor to support this, this diversity of topological requirements in multi-tenant data center? Okay, I'll paste that back, and I'll motivate one more requirement that we have. Okay, and then we'll go further. The other requirement that we have is about this address space, right? So we discussed that these VMs, multi-tenant data centers, have a very specific requirement about the diverse topological requirements, right? What about the physical addressing? Now, I have very strong motivations that I want to be flexible in terms of moving these virtual machines from one location to the other, right? Can I simply do that if I have fixed addressing for, like, if every virtual machine here has a physical address, and if I turn one off and then spin it on some other servers, then will that be a painful thing or will that be an easy thing? Pain. Okay, why is that going to be a painful thing? Okay, so why is it going to be painful? Because first of all, I have to, like each of these servers, like there will be some type of, they will belong in some prefix range of IP addresses, right? So depending on which location I have, the IP address at a different location might change, right? Because I have to be, like to maintain some sanity in my routing tables, I need to group bunch of physical IP addresses together. So if I'm moving from one server to the other, I might have to change the IP address. Now, if I'm changing the IP address, then I also have to change the routing table entries. Like whoever is trying to reach me, they should know that this IP address has moved somewhere else, and there is a new routing path that everybody has to traverse to come to this IP address, right? So it is like, first you have to physically change the IP address, and then second, you have to update the routing table entries such that people can reach there, right? So this is the reason why it is going to be a pain. Okay. Now, like different, tenants who are completely who are basically, like having diverse set of requirements. They want more control, right? So they want this, because when we are talking about virtualization, we are talking about multi-tenant data centers. So we are giving them an abstraction that they are in full control. So when they are in full control, they want to manage how they do IP address allocation, right? So which VM should be allocated what IP address is something that the tenants want to dictate. But if I'm using the physical addresses, that's going to be a nightmare for me to manage, right? Because then I have to restrict, either I have to be support a network where any IP address or any virtual machine can have an arbitrary IP addresses, right? And a physical server will have multiple IP addresses that will all look very different from each other, which means that I will not be able to group them together when I'm writing the routing table entries, right? And which will just explode the number of routing table entries that I will need. So I need some type of order in IP address allocation to the physical servers. But if I do that, then I'm not able to support this requirement that the tenants have, that they want to manage their own IPs. And also I'm not able to support this requirement that they want to move VMs from one location to other, because if they do, then it's going to be pain for me to change the IP addresses for the VMs and then change the routing entries, right? And more importantly, some tenants say that, okay, like I don't want IPv4, I want to use IPv6, and my physical network is only supporting IPv4. How can I do that? Right? So there are these distinct requirements. One approach is that I build different physical topologies, completely different physical networks for different tenants. That is a solution that I can go for, right? And that will solve the topology requirement as well. That like if a tenant says, I want this L2 connectivity, then maybe I should buy a L2 switch and physically connect it to all the servers, such that I can offer them this abstraction that, okay, like all your virtual machines are connected via a layer 2 switch. But that's not virtualization. That is just expensive way of solving the problem, which is never sustainable. So the requirement that we have is that, let's assume that we have a physical network, which we have already invested in. We cannot change this physical network, right? That's very expensive thing to do. Now, how can we enable, like, how can we satisfy all these requirements? The requirements that different tenants or different applications will require completely different topologies, and they will also require completely different address spacing. They want full control over addresses that they're using, and they don't want anything to do with the physical addresses that we are supporting in our network, right? So decoupling the physical and like the address space that we are offering to the tenant is critical, because it is very critical from the requirements perspective, right? So these are the motivations that we really need to think deeply about how can we offer a virtualized network abstraction for these multi-tenant data centers? Because if I have to, like satisfy all these requirements without having a good virtualization solution, then the only thing that I can do is like invest heavily in building these custom physical infrastructure that are customized for different tenants, right? And that's going to be very, very expensive, not an economically, like feasible thing to do, right? So this was one of the biggest motivation for network virtualization, that they wanted to provide this virtual abstraction to the tenants without really changing the physical network significantly, right? Because like one option that they could have gone for was that like there is this new toy in town which is called OpenFlow. So why don't we replace all this existing hardware that we have bought, which is maybe billions of dollars worth of hardware, and replace that with a OpenFlow switch? Maybe that will solve our problems, because OpenFlow is supporting all this tunneling and source routing and all these new features that the previous generation of switches were not supporting. So maybe we can do that, and that's something that a lot of people considered as well. Like it's not a very extreme thought, but it makes more sense if you're creating a new network from scratch. But if you've already invested billions in building a particular network, then that does not really make a lot of sense to replace all these physical hardware targets to support any type of virtualization, right? And what is the other option that I have here? What can I do? So the other option is basically going for the software data plane targets, right? And this is something that we discussed in the previous set of lectures as well, that sorry, this is very distracting. So Open vSwitch is offering the softwareization of data plane, right? And this is very effective, but what is more important is that all this change is pushed to the edge, to the servers directly, right? So it means that I can still work with the physical network that I had and still use these Open vSwitches, which I can program through some OpenFlow controller and provide the virtualized abstraction that is required, right? But just using Open vSwitch does not solve the virtualization problem. We still have to think about what are the right abstractions that we should provide, such that we can, offer this virtualization of both topology as well as the address space. Okay. Any confusion so far? Are the requirements that multi-tenant data centers have from networks, and why do we need network virtualization for multi-tenant data center? Is that argument clear? So Victoria, you want me to repeat the motivation for virtualization for multi-tenant data center, or the question? Okay. So my question was basically, is the motivation why we need network virtualization for multi-tenant data center, is that clear? Okay, great. So, like what I'm talking about here is basically early 2010s, around say 10 years from now, this was a time when all these companies like Google, Microsoft, Amazon, they were all scaling up their cloud offerings, right? And they were supporting, they didn't start offering cloud as a service to other tenants. They just started cloud, building these massive data centers to just scale up their web applications or their service offerings, right? So when you think of Google or Microsoft or Amazon, they require heavy compute, right? So when you think of these search engines, you are interfacing with these search engines through the gateways, and then at the back end there's a massive set of servers that are sitting in crunching numbers to figure out what is the best order in which your search query should be responded, right? So there is a huge compute requirement, right, that was going on there. And as these networks were scaling up, they were just trying to come up with new and new applications. And when they were coming up with these new and new applications, then they realized that there were these differences in the compute requirements, which translated to differences in how they want the network to behave for them as well, right? So this was an intrinsic like diversity of requirements from the network that different applications had that motivated network virtualization. But this was also the time when all these companies started realizing that we have invested so much that we can actually make money out of it. And that's when I think, like AWS and Google Cloud, like Google Cloud was not the first that came out. Maybe the ideas were there, but I think Amazon AWS was something which, like explored this idea of offering all these compute resources that we have built for our in-house compute requirements. We can actually sell them because a lot of them might be just sitting idle for a lot of time. So like maybe it is possible for us to rent it out to some other, customers who can just use those compute required, resources on demand, right? So this was a phase around 2010, 2012 when these developments was going on, and that's when the multi-tenant data centers kind of like started gaining traction in the mainstream community, right? Because there was a bit of a commercial use case that people saw, that we have these different applications, or maybe completely different tenants who will be sharing these compute resources. They will be sharing the physical network, and we really need a good solution for network virtualization. And this resonated well this resonated well with all the other developments that were going on in the networking community. So recall that the first set of ideas that people had for software-defined networking, they were more focused on the enterprise network, right? So you can think of them as focusing more on the requirements of their campus network, that they have campus network, you need to support VPNs, you need to support load balancing, you need to support authentication services for wireless users. So there were a bunch of different applications, and the networking researchers were thinking about providing network virtualization for those type of requirements in the network. They were not really thinking about data centers, but the core set of ideas were emerging and developing, and the requirements that came from these cloud or content providers perspective just basically pulled all these ideas in, and then converted them into some really useful commercial products, right? And one of those products that we are going to study today is called Network Virtualization Platform, NVP. So the NVP was basically started by a core team of researchers from Stanford University who were all behind the concepts of open flow, OVS, and everything out there, right? And then they realized that, okay, there is a commercial opportunity out there, that there is this growing trend that we will have these different type of tenants sharing the compute resources. Virtualization for compute is out there, but virtualization for network is not out there, right? And then they realized that, okay, we need some type of virtualization layer. So they basically started working on it. They started pushing the ideas that, rather than starting by asking everybody to change their physical network, let's start by changing the software stack, right? So let's change the software in each of these servers such that they can offer programmable control over the network. And then we can think about in the future, a world where we can also change these, devices in the network, as well as converge that with the virtual switches, right? So this is kind of this is what the future looked like. But then, this was a great opportunity. And eventually, if I remember correctly, Nisira was the startup that was created around these set of ideas, and it was acquired by VMware for a couple of $1 billion. I don't know exactly. I don't remember exactly. That was a public information. I don't remember exactly. And all the folks who were involved in software-defined networking, OpenFlow, key folks from Berkeley and Stanford and Princeton, they were kind of involved in that, and they benefited a lot from the commercialization of this idea as well, right? And that commercialization basically pushed, provided momentum and impetus for all the other ideas that were not really making a lot of commercial sense back then. But then it helped create these open source community that just provided an environment or a catalyst for all these new innovations to follow through. I mentioned something about Open Networking Foundation, which was kind of in the same like a spectrum of things that when Nisira was sold, there was a lot of money, and a significant chunk of that money was pushed into these open source efforts, and that just catalyzed a lot of changes in how we think about networking, right? So I just wanted to share that perspective with you, because what we are going to read is a good story of academic ideas getting translated into some commercial success, and how that success basically funded or catalyzed the innovation in this research area. Okay, so NVP is very much in line with our view of what a network virtualization solution should do, right? It is a layer that is sitting between the control programs and the operating system. It is providing an abstract view of the network to these control programs, and it is responsible for translating configuration changes made to the abstract view to the physical network, right? So this is exactly what NVP is supposed to do, but it is designed from a multi-tenant data center perspective, right? And it makes a very specific choice that rather than aiming to make any changes or configuration changes to network devices of the existing physical network, it only forces changes on the edge of the network, which is the virtual switches on each of these physical servers, right? Okay. So now, as I always emphasize, that abstractions, right? So abstraction is very important. And when we think about NVP, what is the abstraction that it is offering? And what is different about NVP's abstraction compared to maybe some other solutions that are out there, right? So NVP has two main abstractions in play. One is the control abstraction, and this control abstraction is for the tenants. The other is the packet abstraction, and this is for the packets that are sent by the endpoints or the VMs to get this, to get different type of services. So let's talk about the control abstraction. As I said, that in context of multi-tenant data centers, there will be different tenants that want a different, abstract network that they want to operate on, right? So as I said, if I am an enterprise tenant, right, and I want to make sure that all the VMs that I have, they're all directly connected to each other over a layer 2 switch, right? So that is a network. I basically kind of want a hub spoke model where I just have one switch and all these virtual machines are connected to it, right? So this is a topology that I want, and I want to completely control not only how these VMs are going to talk to each other, but maybe I also want to apply a network function or a policy where I want to maybe say do some type of firewalling, right? So I can say okay, half the one half of the VM should not talk to the other half of the VM, right? And this is a control that I want to enforce in my network. But for that, first I need that app, the view, the topological view, virtual topology that I need to view, and then on top of it I can apply whatever control logic I want to enforce in my network, right? So the control abstraction, the key idea there is that when we offer this abstraction to the user, they should not they should basically get all the control that they would have if they had their own physical network, right? So if these tenants had a physical layer 2 switch and they connected all these VMs with each other, and the way they would program that physical layer 2 switch is how they should be able to program this virtual layer 2 switch, right? So this is the control abstraction that NVP is offering to its tenant, right? And the network hypervisor here is the one that is providing the control plane implementation for the defined network elements, right? So basically the tenants can define a set of logical network elements that they want to configure, and they want that configuration to be exactly same as they would do for the physical network, right? And the network hypervisor is the one that is enabling this type of realization. What is packet abstraction? Now the packet abstraction is that the packets that are sent by the endpoints, these VMs, they get the same service as the physical one, right? So if the tenant has expressed a policy or has expressed this configuration where it wants that this has to be a layer 2 switch, or maybe it has to have a firewall and has to have an ACL, right? So a packet abstraction is that this packet which is going through this virtual network should go through the same sort of, or should get the same service, right? It should go to the firewall, it should go to the ACL before it can reach to the other VM, right? So the behavior, the handling, or the treatment to the packet should be exactly the same as the treatment it will get in a physical network. Okay, so this is the packet abstraction that is for the packets which are sent or received by the endpoints. Okay, all right. So this is a good time to take a pause and think about is this concept clear? Is the control abstraction that is offered to the tenant and the packet abstraction that is offered to the packets from the endpoints, is that clear or not? Yeah, I don't know, like level one, I don't know, or like if I can say it is a switch, but level, like it's not really level two, these are layers, right? So the layers that we have in networking. So layer two is basically the medium access, or this the Ethernet layer in context of wireless networks, right? Layer three is basically the IP layer, which is used for routing. So when a particular tenant wants just layer two networking, basically it wants all these machines to be directly connected to one switch, and they can just talk to each other without requiring any IP addresses, right? So they can just look at the MAC address and say like, okay, forward this packet to a particular MAC address, right? Is this answering your question? So yeah, layer one is physical. I don't think anybody provides an abstraction for layer one, though the abstraction for layer one can be more relevant in context of 5G networks, but that's a bit beyond the scope here. But in context of multi-tenant data center, there is no notion of layer one, because that's a physical network, right? So in 5G networks, or in like the last mile access network, we can actually provide a layer one abstraction as well. That like, is your network or is your traffic going to go through cellular link or a Wi-Fi link or a cable link, right? So all these type of options are out there, but that is completely irrelevant from the multi-tenant data center perspective. Okay, so I think given that we are running out of time soon, I just want to maybe use this example, and we can revisit this example in the next lecture as well, that we're talking about this yellow tenant, right? So we had these different colors for the VMs. We are talking about this yellow tenant, which is interested in providing an abstraction, or like it wants a virtual network which has a layer 2 switch connected to a layer 3 router connected to a layer 2 switch, and the VM here, or the set of VMs are on the left are connected to the left L2 switch. The set of VMs on the right are connected to the right L2 switch, right? And this is like, so L2 switch, L3 router, L2 switch. This is the topology that the yellow tenant wants, right? And right, so this is different, or this can be very different from what the physical topology looks like, right? But NVP is able to provide this abstraction to the control abstraction, right? So control abstraction, it will basically, it can define the set of logical network elements that it wants to configure, and can define how exactly it wants to configure them, right? And then the packets that are going through will basically get the same treatment as if they are going in this network, where they have to first traverse a layer 2 switch, then they have to traverse a layer 3 router, then they have to traverse a layer 2 switch to finally go to this other VM, right? So I think maybe all these things are not 100% clear right now. We will revisit them again. But I think, like what I really want you to take away today is that when we talk about these multi-tenant data centers, they they have very distinct requirements from the network. And a physical network, it's really impossible to realize all those diverse set of requirements by just having that, relying on the physical network. So the idea that NVP had was that, okay, let's provide a virtualization of this network. And to do that, what they focused on was, rather than like changing or requiring us to change the entire physical network, let's just change the edges, right? Let's just enable these virtual switches on the physical servers, and then provide all these two, abstraction, which is control abstraction, packet abstraction. How this is going to get realized is something that we will discuss in the next lecture. And what are the scalability challenges associated with it is also what we will discuss in the next lecture. Okay. But I'm hoping that, like the key gist of why we need it is getting clear in your head now. Yes, yes. So I think Garrett asked a very good question that it's NVP, not NVM, right? So NVP is the one which is enabling, like, you can have Twitch as one tenant and maybe, like Hulu as other tenant. And Twitch can explicitly express that what network it wants and how exactly it wants different VMs that belong to Twitch to be connected to each other. And then it can write a control program about, like what type of access control policy it wants to implement, what type of firewall policy it wants to implement, maybe what type of load balancing policy it wants to implement. So it can express all those policies as if it's a physical network, but it's a virtual network that is realized over Amazon's physical network. Okay. All right. So I hope you find the topic of virtualization interesting. I think, like this is something which is both intellectually interesting, but also, it is like broadly applicable in whatever networking you do. So, pay special attention to networking. You go out in industry, you might not be exactly working on multi-tenant data centers, but like virtualization is something that is very fundamental when it comes to networking, and trying to get hold of virtualization as much as possible is going to be critical if you do anything closely related to networking in the future. Okay. All right. So talk to you folks next week. I actually want to let you know that, or maybe this is something which is very important. I should have talked about it earlier. So as I mentioned in the last lecture, that I'm still suffering from, this sciatica nerve issue, that it's very hard for me to stand for more than 2-3 minutes at a time. So I'm hoping that things will get better in a week, but I think like the Monday lecture, I will still try to keep it online. And I don't think I can do the lecture on Wednesday. So, we can adjust that lecture later. I might be, so I have some appointment with the doctor on Wednesday. I'm hoping that, things will get better. And next Monday, which is, like next to next Monday, which is February 7th, we'll all meet in person. But next week, I think like, I'll still keep things remote, right? And especially with the also, like from TA's perspective. So, that the TAs were traveling to their respective home countries, and they are back, but I think they will be in a bit of a period of isolation of the international travel. So next week, I think the TAs, the discussion sections and office hours will still be remote. But I think like from February 7, we can all expect that everything will be in person. Okay. Any of you have any concerns, just let me know.